There we go. All right. So, right, we left off our notes on at this point right here, just talking about this idea of a circuit, right? Voltage is the battery, or in case of our lab, a power supply that varied the voltage. Resistance in our lab was the light bulb or the number of light bulbs, and then the current flows out of the power supply through the light bulb and then back to the negative and the low potential on the power supply. All right. So that's where we kind of left off. One thing I want to note here before we move on. This is the conventional way of describing a circuit, right? The high potential of the positive terminal on the battery. So it's the high potential, so the current leaves the high potential and flows through the circuit to the low potential. So essentially falls from high potential to low potential, right? And that's the convention of how we describe circuits. But in reality, it goes the other way, right? Because the high potential would be positive here, and to have high potential energy, you'd need positive charges. So you need protons. So the protons would have to move through the wires to the negative end. Protons don't move. They're stuck in the nucleus. So in reality, what happens is the opposite. The electrons move from the low potential to the high potential. Electrons actually move, right? And if we think back to our energy formula, right, U, right, energy is equal to voltage times the charge. So the low potential or the negative potential terminal times the negative electron has high potential energy, is a positive potential energy. So it flows from the positive potential energy, the electrons actually flow from the high potential energy to the low potential energy of positive times negative energy, right? It's dumb. I don't know why we do it this way, why we describe the circuit going this direction as opposed to the other direction. But the convention says we go from positive to negative, but in reality, electrons go from negative towards the positive. All right. Everyone follow along on that, what I just said? We good?
Yep.
All right, let's take a look at, oops, why am I not going to the next slide? There we go. Ohm's law. In the lab, what I was hoping to find is that V, which we put on our y-axis, and current, which we put on our x-axis, had a direct relationship, had a linear relationship, and then the slope of the line would be r, right? Because y equals mx. So y was the voltage on the y-axis, current is on the x-axis, and then r would be the slope of the line. And I'll be honest, I was a little bit lazy and didn't look at your labs yet, but I did talk to Dylan yesterday, and he was showing me the data, and the data really was not linear. And I'm not sure why. I have a suspicion as to why, but I'm not sure why the data wasn't linear. The data was more parabolic. Some of you kind of forced a line in there. So you should have come up with this formula. Probably had some, ideally the y-intercept should be 0 because 0 voltage gives you 0 current. But we get this equation. All right. Like I said, I'm not sure why I'll talk about on the next slide why I think the data in your lab actually came out to be a little bit parabolic. But this is what I was hoping to get out of the current, is this equation, right? Voltage equals current times resistance, or V equals IR. Okay. Obviously, I is the letter we use for current here. Good? All right, you can see there are two examples. It says on the slide, I'm going to read through them. They're very simple, but I want to cover, I want to use it as a point of emphasis here. All right. So I'll just read it. If you don't have your book open, it's real simple, like I said. The first example, a small flashlight or a flashlight bulb draws 300 milliamps. Amps is the unit of current. So 300 milliamps from its 1.5 volt battery. Part A, what is the resistance of the bulb? That's obviously just plug and chug. You're given voltage, you're given current, solve for R. Simple, right? It turns out to be 5 ohms in this case. In part B, though, this is what I wanted to emphasize. It says, if the battery becomes weak and the voltage drops to 1.2 volts, what would the current change, or how would the current change? I can't read, apparently. The point I wanted to make here is that when we solve it this time using V equals IR, we have a new voltage. Resistance doesn't change. Resistance is a characteristic of the device. It has nothing to do with the energy going through the device, the charge is moving through the device. So that 5 ohm resistance we found in part A is the same 5 ohm resistance we have in part B, right? The light bulb has a resistance, and it's a characteristic of the light bulb. It has nothing to do with the battery lighting the light bulb, all right? And that's what I wanted to emphasize, that once you have R, you have R on a given device, right? The resistance is not going to change, okay? If it's an ohmic device. I'm going to now look at the second example, conceptual example, and that kind of brings us back to this. Here's this device. Here's the system, and the current's going through. So which end of the resistance of the resistor has a higher potential? All right. And the higher potential, we go back to our power supply. So positive end of the power supply, positive terminal of power supply, has the high potential. So it's closer to this end, the top end of the resistor. So the top end of the resistor has the high potential, and the low end of potential, if you follow the wire back, is closest to the low potential in the negative terminal in the battery. Okay. And potential drops as the current goes through the resistor, right? Go from a high current travels through the resistance, the potential drops from the high to the low potential. And sometimes you'll hear that term of a drop, right? The voltage drop or a potential drop. What was the voltage drop by a resistor or through a resistor? And that's what we mean by a voltage drop or a potential drop. As the current goes through, the current goes from the high end to the low end in terms of potential. All right. Part B says, is the current greater at point A than point B? So is the current greater when it goes into the resistor or when it comes out of a resistor? Okay. So the answer to that question is the current's the same, right? We have conservation of charge. Imagine a lot of current going into the resistor and then getting stuck in the resistor. It would all kind of have this giant traffic jam. And if only a little bit came out. That can't happen. So the charges that are moving in, the same amount of charges have to move out, right? Right? Could you visualize a lot of charges moving into the resistor, hitting this resistance, slowing down, and only a little bit coming out? You'd have this giant traffic jam of charges. That can't happen. All right, so current is the same everywhere. All right, any questions so far? All right, silence means no questions. All right, last thing to cover, this idea of resistance. Okay, like I said, the resistance or resistivity of a device is a characteristic of the device. So it has nothing to do with the battery or anything. So we have this new formula here. Resistance equals rho times length over area, right? In a device. If you can imagine, which kind of makes sense, the rho is a constant of proportionality, right? As you can read. And there's a list of all of the resistances of the materials that we're going to be dealing with in the book on page 501. But length and area, if you can imagine, going back again to my picture, the longer the resistor is, the longer the wire is, the more opportunity that those electrons that are moving through the wire have to collide with nucleus of that metal wire, of all those metal nuclei. And the more collisions, the harder it is to get through, right? It's effectively, resistance would be electrical friction. So the longer the wire or the resistor, the more collisions that the current can potentially have, the higher the resistance. All right, directly proportional. Inversely proportional to area. The wider the resistor, the thicker the wire, there's more space, cross-sectional space for the current to pass through. So it's easier, right? Think of us walking through the halls of Ben Salem or walking in the doors when we're all coming in after a fire drill. If we only open 2 doors, it's hard to get all of those thousands of kids through the doors and back into the building at the end of a fire drill. But when we open a whole bunch of doors, it's easier. There's more space for us to travel through, less resistance. We're able to get through and into the building easier. Same idea here, right? Okay, which brings me to the last statement. Resistance also varies directly with temperature, which is my theory as to why our lab turned out to have parabolic data. The longer we left the light bulb on, the hotter the light bulb may have gotten. And as a result, the resistance increased, and then the slope of the line, or in this case, the curve on our graph in our data in the lab would have increased also and gotten steeper. So this is my theory, right? The resistance also varies directly with temperature. That's my theory as to why our lab ended up giving us more of a parabolic shaped graph than a linear graph. Okay, I was not expecting there to be a significant difference in resistance with the greater temperature of those light bulbs, but maybe that's what it was. That's my thought as to the reason we got the data we ended up getting. Okay? Does anyone have any questions at all about what we just covered, the couple of things we just covered? No? We're good? All right, guys. So, like I said, if you look on, I'm going to stop the recording here.